Swayam Prabha. Digital India. Educated India.
Welcome back. In module 7, we will start supervised learning, and this is part 1, and of course we will have supervised learning over 2 modules. So lecture 31, we will introduce supervised learning and also linear regression as well. So the different concepts that we will cover will be, we will again revisit machine learning models in general, then we will talk about supervised learning, and within that we will talk about both regression and as well as classification. Then we will discuss the sklearn or sklearn functions and objects for this particular library. Then we will define a ML machine learning problem, how to look into it, what is theory building, what is model choice, and then we will do linear regression where we will train and test. We will split the data into train and test, and we will do data processing and so on. And finally, we will do model training, prediction and evaluation. So we are revisiting this slide which we have already discussed earlier. So there are different machine learning could be divided into many categories. Primarily it is supervised learning, semi-supervised learning, unsupervised learning and reinforcement learning. And of course, neural network could be applied in any one of this. But neural network has been kept separate because usually it itself is a it's a way in which we do machine learning problems. So in this particular lecture, we will be focusing on the first part, that is the supervised learning part, and usually these are the 3 tasks: regression and classification. Dimensionary reduction could be also done, but that's not very major in this. The most important thing is regression and classification. So what is supervised learning? It uses when we use historical label data to learn predictive relationships, that's supervised learning. So what is historical data? That means we have data from earlier periods. Label data means we know the outcome, and we using this the actual data, the features and its outcome, we can predict different relationships. Now, label data is a set of input data and its corresponding correct response. So both are there, and part of this we will reserve for training the program and part of it for testing in future. And during training, the algorithm has to generalize or form rules so that it can correctly respond to all possible inputs in future. That means first I have to train the model, and training the model means I have to create a set of rules either in form of a equation, or there could be some some rules as such as well, and where the rules should be such that it could be predict something from, if I give you some other input, that model would be able to predict the output as well. Using these rules, the program should produce proper outputs for input cases not encountered during training. So that is the goal of doing machine learning in the first place. So over here you can see we can have different kinds of training data. That means it could be text, images, sounds and so on. Our first job is to extract the features from there. Like for example, we can what we do is whenever there are it's a 2D dimension or a 3D dimension, it means that the distance from the axes x and y axis in 2D is the distance of the weight of those features for that particular point, right? And a point can have many features as well. And similarly, if it's a 3-dimensional place, then this actually increases. Now, first job is to extract the features, and then because it, as I told you earlier, machine learning uses numerical data, and then then I use machine learning algorithms to see which one best fits this particular features, and then once I do that, I try to form an equation out of this, or I want to generalize, and then that results in the trained model. And then what I do is for new data, or like for example text, image, sound, again I have to do feature extraction, and then once I have done that, that means once I have vectorized the features and all, then again I will apply the model which was trained earlier, and this trained model would be able to predict for this, the outcome for this particular set of new data. So that means in this case we are using a trained model, and then we are able to predict the outcome even though we don't know this, right? But to train the model we need to know for other samples that already the labels we already knew. That's why we are able to train this particular model. So in this case what you can say is, along with the training data we also know the labels as well. So that means labels were also part of that, but here labels were not there. So this is the difference. Now there are two kinds of supervised regression primarily, that is regression and classification, but of course we have got dimensionality reduction as well, which is also supervised. But primarily we usually use this regression and the classification tasks. Those are we would encounter those mostly. Now regression is the process of estimating a function that best approximates the relationship between variables in the presence of noise. And so of course that's why the regression can be referred to as a function approximation. That means we are approximating a function. Exactly we cannot, right? Because there would be noise, there would be some, it exactly cannot match, the data points. So the function is fitted in such a way so that it minimizes the overall error, that is the actual predicted as well as the difference between the actual values and the predicted values. It cannot pass through all the points, it may pass through few points, and it explicitly allows noise, measurement error and unobserved factors, which actually play a role in determining the outcome. So if I say that y cap is equal to fx, that means in linear regression it learns a function which is this one, and it should be learning in such a way so that it minimizes the total error. That is, in this case we use the least square concept, where y is the actual and y is, cap is the predicted ones. The difference, we take the difference of that and then we take a square of that, because to take care of the negative signs and all. And wherever this value is minimized, that's the best possible that equation that is explaining this data. So that is the way we go ahead and determine linear regression equations and all. So regressions will predict the continuous values, and there are different regression models: linear regression, ridge and lasso regression, random forest regression, gradient boosting regression. So this we have discussed earlier as well. Out of these two we will learn, while we will learn about decision trees and its ensemble techniques. So these are usually used for classification task, but also could be used for regression task as well. Now dimensionality reduction is basically LDA, linear discriminant analysis. This is one example of it. What it does is it reduces the number of input features using both predictors and the class labels. Now what it means is it retains the dimensions which are most relevant for the class prediction or class separation. So that means it will unnecessary features and all will be removed, and this actually, if you remove that, then it improves the model performance, interpretability, and also it helps us to generalize the model. And it is commonly used before or within classification and regression models. So it is basically an intermediate step, but of course it itself can also predict. But what it means is when we are doing LDA, we are actually testing different combinations to see which one is predicting better. So obviously it is predicting, but basically we do this before actual regression is undertaken. Using this technique, I can reduce the number of features which will go into the main model. So supervised learning again could be another main way we can what we can do is classification. So it is a supervised learning task in which, given an input feature vector, the goal is to assign the example to one of the n predefined classes. So that means here it's not a continuous variable. We are taking n classes, and I can predict which class this particular new instance will belong to. So each input example is represented by a feature vector like this: x equal to x1, x2, xp. So different vectors are there for each example, and the output is a discrete label class, and each example typically belongs to exactly one class. So this is one, of course, assumption that we have to go with, and the set of classes is mutually exclusive, no overlap between classes, and also collectively exhaustive. That is, every possible output belongs to one of the classes. So these are the two assumptions that we have to start with. That is, there is no overlap between the classes, and every output, actually every possible output belongs to at least one of the classes, right? So classification works by learning decision boundaries in the feature space that separate different classes. Now sometimes this could be a line, sometimes it could be a curve, or it could be a hyperplane. That means we have got different points in a 2D or a 3D space. If it's in a 2D space, a line can differentiate between different classes, or sometimes it could be a curve instead of a line if the data is based on a distribution of the data. But suppose it's in a three-dimensional plane or even a higher dimensional plane, then we have to separate it by a surface or a hyperplane. So each region corresponds to a particular class, and a new input is classified based on where it falls. What we do is we have to train the algorithm, and it learns to identify critical combinations of features and different feature values for each class, which would help us to identify what will be part of that class. And this learned differences define the decision rules that we finalize. The choice of the classification algorithm depends on many things. That means which algorithm will you choose, because there are several classification algorithms, decision trees, KNN, then there is logistic regression. Which one will you utilize? So it depends on the nature of the data. Is it is it depending on how is the distribution of the data? Is it linear, non-linear? Many things. The nature of the data will be considered first. Then the shape of the decision boundary required, that means is it a straight line or is it a curve, linear or non-linear, that part is required. Then the level of interpretability needed. Not all models, most models will be able to predict, but can I interpret the model, that is which features are important, which is not. So that part, if some models would be able to do that, other models less. Trade-off between accuracy and computational complexity. Sometimes what happens, if the computational complexity is more, it takes more time, more CPU power. So sometimes it is a trade-off between accuracy and computational complexity. And these are some of the common classification models like logistic regression, k-nearest neighbors, support vector machine, decision trees, and random forest. This we will demonstrate all of them after this. So coming to one of the most important libraries, the machine learning library, sklearn library, we can look into some of the functions or the objects, the classes and functions that it offers. For example, it offers this we can first of all, sklearn offers a lot of data as an example which you can utilize to test the different functions. There is the IRIS data set, the wine data set, California housing data set. All these things are there, which you can, these are example data sets included, which you can call to test various algorithms, or you can see how this thing works. Then there is a train test split and k-fold. So these are validation techniques. And then we can do scaling, that is standard scaler actually scales the data into either normalizes the data by either taking the z-score or the minimum maximum. So then stratified k-fold, that means we can divide the data into different groups, and then we can train the model on that. And then we can do minimum maximum scalar. Then we can encode the variables. For categorical variables, we can use a one-hot encoder or label encoder to convert them into dummy variables and all. Then we can impute data, that is missing data could be replaced by simple imputer or KNN imputer. Then we can select different features using various threshold like the variance threshold, or select k-best, RFE, and so on. Then different regression tasks, supervised regression tasks, we can do linear regression, ridge regression, lasso, support vector machine, random forest regression, and so on. For classification, we can go for logistic regression, k-neighbors classifier, decision tree classifier, random forest classifier. Then for clustering algorithms, we will learn about k-means, dbscan. So these are unsupervised, of course, so we will learn that later. And then agglomerative clustering. For dimensional reduction, we can go for PCA, kernel PCA, truncated SVD. Then for manifold learning, this TSNE and isomap. So it is for nonlinear embedding and visualization. Then ensemble learning techniques, that is, these are variants of random forest, variants of decision tree, random forest algorithm, gradient boosting algorithm. So this again we will demonstrate later. And then different model evaluation metrics such as accuracy score, F1 score, ROC AUC score, mean squared error. All these things could be also determined using this particular library. Then along with that, model selection and tuning, grid search CV, randomized search CV, cross-val score. So these are all, where we can do cross-validations and hyperparameter tuning. So this we will demonstrate eventually when we discuss the different algorithms. And then we can create pipelines, and we can also, use column transformers, that you will see again demonstrated that pipeline actually help us to create a series of steps together, and we can call those steps together using a pipeline. Then nearest neighbor algorithm like k-neighbor classifier, nearest neighbor classifier, this this kind of models are there. Probabilistic models like Gaussian mixture, neural network models are there. Then outlier detection functions are there, and finally we can fit the model using the fit function, predict function, and these are different. Then transform function actually can transform some of the features and all this are part of the sklearn library. Now coming to an example of a linear regression model, we will also do linear regression in much detail later, but this is a typical machine learning problem. That is why we wanted to demonstrate it. So let us try to determine the number of trips generated from a traffic analysis zone. That means we have the city, and the city has got different, we can divide the city into different parts. We now need to predict how many trips are generated from each of these TSZs. And it could be based on the different zone level characteristics, right? So in this case, the dependent variable is the total trips generated per zone per day, which is y. And in this case, the independent variables, which is given as x, are either the population which lives in the zone, urban form parameters like area under different land use, or the area under different building uses, then accessibility parameters and so on. But we can have different specifications of the model, but here we will test one to show you how it works. So we are using this particular data set, trip_gen_model_reduced, and you can see over here the different the features you can say are of course this is what we are trying to predict, total trips generated. Then there is population M, population F living in that particular zone. Then ARRESI is basically the residential land use area. Then ARCOM is the commercial land use area. Then floor area residential is the total built up area under residential. Total floor area commercial is the total floor area under commercial. Then the total area of roads and the transit station distance, these are the more accessibility parameters. Now why these are accessibility? Because the more is the area of roads, it means like it is more accessible or people can move easily. And similarly, transit station, if it is nearby, then of course we are getting access to transit, and this area becomes accessible. People can come from many locations using transit, and they can, because the transit station is nearby, they can access this easily. So this is the CSV file. You can see that these are the data which is there row wise, and we have just converted that into Excel for your understanding. You can see in one side we have trips generated, and these are the different the predictor variables which we are actually using. So we are also taking, in addition to accessibility, residential density and commercial density. So density means total area divided, total built up area divided by area of that particular land use. So commercial built up area divided by total commercial land use area. So usually trip generation models historically has been linear and log linear forms. That means how we know from literature. So whenever we are building a model, we should know, from literature, what sort of models have been built earlier. And this actually we know this. So now we are trying to develop a model. We will like to follow similar approaches. So trips are generated by people. So this total population could be either male or female. Then land use area, horizontal spread, floor area, vertical intensity, and density, which could be a interaction term. That means density actually contains both land use and floor area. So maybe if I take all three of them, it will not work because they would be collinear, right? There will be multicollinearity. But if only I take floor area, then I am missing the aspect of how much land use is there. If I am taking land use density, this total floor area could be very varying, right? That means land use could be a fix, but because FAR value is very high, the amount of people who would be staying there is very high, and that would lead to larger trips. So instead, density, because it is taking into account both of these attributes, it is a better term to consider. So accessibility also influences trip propensity, that is transit distance, road area proxy. So this is what we have taken. And so what we are doing is we have to select which model we are going to utilize. So even though I am demonstrating a linear regression model, but let us assume that I am not demonstrating a linear regression model. I am demonstrating what kind of model should be appropriate for predicting trip generation. So because trip generation has been usually done in linear and log linear forms, we are choosing linear regression. So aggregate trip generation often shows an approximately linear relationship with population, land use, intensity, and accessibility variables. So that is why we are choosing that. Now, also this makes the model easy to interpret for planning and policy analysis. Why? Because as we know that if the predict y equal to beta 0 plus beta 1 x1 plus beta 2 x2. So this is the linear form, right? So if I can determine beta 0, beta 1, beta 2, definitely we can determine that how important is this x1 or x2. So accordingly we can decide what to change to reach that value of y that we want to. So that is why it becomes important for policy analysis. That means what policies should I change or what things should I change so that I can reach the results I desire. So some assumptions before we build the model: the relationship between predictors and trips is linear. Errors are independent with constant variance. That means homoscedasticity property is followed. Predictors are not highly collinear, and residuals are approximately normally distributed for valid inference. So this error term, that is this the residuals would be approximately normally distributed. So trips I is for ith zone is equal to beta 0 plus beta 1 into population plus population I of population zone I, and beta 2 residential area of zone, and so on so forth. So there could be, if I take all the variables here, that is residential area, residential land use, density, there may be multicollinearity. So because floor area and land use area are linked, and that's why we may not use we could go for multiple model specifications. Like we can go for model A will use population, land use, and accessibility as the predictor, whereas model B could be population, floor area, and accessibility. Model C could be population, density, and accessibility, and then we can actually test which one gives us the best results, and that one we can choose, right? So the goal is to predict trips using a linear function. This is the linear function, and what we are trying to do is we are trying to fit the best possible, we are trying to find the best possible value of beta or betas, so that we arrive, that means y value, the predicted value is as close as possible to the observed value. So that is what we are trying to do first. The error for each observation is the difference between y1 and y1 cap, that is between predicted and observed, that is E1 is equal to y1 minus EI equal to yi minus y cap I. So what we are trying to do is, that means we want to reduce this. Now to do that, we take a square of that and we take it over for all the prediction points, that is I equal to 1 to n. And so this becomes our loss function. That means we are trying to optimize this. That means we are trying to minimize this sum of squared errors, and that's the values of beta which minimizes this, that will be accepted as the solution. So coefficient are chosen such that the total squared difference between the observed and the predicted trips across all zones is minimum. So we can start with the initial guess for beta, and beta is then adjusted following some strategy to reduce the overall loss function, the overall loss, which is in this case L, and then stop when loss cannot be reduced further. So this is where it is the minimum loss, right? So that means it is the least amount of value. So that would be the final where I stop the beta values, and those would be the beta values we will accept. So so the model in this case, the equation is a linear form. The learning optimization actually minimizes the loss function, in this case this one, and then generalization is low loss on unseen data. That means once I predict this, use this particular equation with these beta values that I am getting over here, I will be able to predict for a new case, and that is the process of generalization. So that means the difference between the predicted and the actual value would be very less, and that's the purpose. So that means the model would be more generalized if that is the case. Now coming to the example in Python, so we are importing pandas as PD, numpy as NP, and then we are importing linear regression from sklearn, but along with that we are also importing train test split, then we are importing simple imputer, then we are importing standard scalar, and then we are also importing the different matrices which are R-squared score, mean squared error, and mean absolute error. So these are the three matrices that we are using. So mean squared error, root mean square error, then R-square value, and then the MSE value, MAE value. So first we are loading the dataset trip generation model from my drive D into the data frame DF, and then I am predicting which is the target variable, which is total trips generated, the features variable, and we are also choosing which are the features variable. Then what we are choosing is that means in x equal to df features, we are actually choosing this as the features, x becomes the features and y becomes the target, which is the target variable, that is total trips generated. Now then I train the model, we divide the model into following this test size of 0.30, which basically means that 30% of the data would be reserved for testing, and random state 42 actually means that again and again when I do the splitting, the same split will happen because of the random state is fixed, right? And then once we do that, then we divide the data into x train, x test, y train, y test, and then x train and y train are the ones which we use to train the model, and then x test would be used to predict the model, and the prediction would be compared with y test to see if our predictions are correct or not. So then we are using a imputer, simple imputer, strategy is medium. What it does is it takes all the values of x train and sees if something is missing, then it transforms it by putting the median, right? Because that's the strategy what we are using. Same goes for x test as well. So for both x train and x test, we are removing the empty values with their median values. Then we are using standard scalar, which is to scale the features. That means linear features are scaled using the z-score, and then once we do that, so that means once we decide that we are going to go for the standard scalar, we are scaling x train IMP and x train x test IMP both, and we are storing those those values, and then we are calling the linear regression, and we are alert.fit is actually we are passing x train scaled and y train data, so that we are able, this is the y value and this is that scaled x values, right, the feature values, and then we are predicting y underscore predict stores alert.predict, that is it predicts on the test set, and then it is stored. And then we are also predicting the R2 scores based on Y test and Y predict. That means we are taking the predicted values and the actual values and trying to determine what is the R score. And similarly, we are determining RMSE for the Y test and the Y pred, and Y again MAE as well as mean absolute error is also determined for the test, Y test and Y pred. So we are predicting the values on the the data that I kept aside, and then I am comparing with the actual values to see what is the difference in the prediction. So then once we have done that, then I can print the value of R square using F streams, then RMSE values, MAE values and so on. And then you can see over here R square, RMSE values and MAE. And then what I am doing is I am determining what is the median for all the I want to predict the data for the I take a hypothetical median word, that is for all the words that are there. Like I take one of the words, it's a median word, and I am trying to predict what would be the trip generation using this model for that median word. And that is what has been done over here. And we have predicted that predicted trips for a median word, it comes to around 28396 trips per day. Now just to give you details, this is the formula for R square. So it compares actual values Y test with predicted values Y pred, and R square measures how much of the variation in the target variable is explained by the model. So Y minus Y cap is the variation, and how much of that is explained is actually being shown in this is actually demonstrated by R square. RMSE root mean squared error computes the average magnitude of the prediction error. That happens like this. And then MAE mean absolute error is computed, which computes the absolute difference between actual and predicted values. So this is how we can predict MAE. So once these three things are there, we can understand how good is our model. So this R square value of 0.6663 actually means that around 67% of the variation in trips could be explained by the model. So that means there may be requirement for other variables that has to be included to do more better predictions. So these are some of the references that we have used. And to conclude, linear regression illustrates the core machine learning principle that learning is an optimization process, selecting model parameters that minimizes prediction error while generalizing to unseen data. Thank you.